great. Everybody ready to go. Shall I do it? I shall do my block. And return. And return. Check this. Check this. Yeah. Agree and time to show something. I have something here. It's there. It's a funny. Toy. I made it. I checked. I made this thing 16 years ago.
Oh.
Can celebrate birthday. What is it? It's a rheostat.
Okay.
Usual rheostat, but with drive. And it has a control system. What's the system? Two channels. This model converts analog values into digital. It's analog to digital converter. One channel powered from this small rheostat, it's a set point. And another channel with this converter receives a load voltage. So rheostat is loaded with 3 volts. The control system, wait 1 second, I might try to get it on the screen. Come on. One thing I will burn this TV. Yeah, here it is. It is mine. Try to show it. It's a control. What's going on inside? It has 2 channels. One is voltage set point. I can change it. And another is a measured voltage. And this logic tries to keep them equal. It changes. You can increase. Goes, measure it until they're equal. It's one moment because I cannot set voltage absolute precise. Winding has a step. So that zone of 16 relative units is introduced here. If I change load, I drop load completely. See what it's doing? Go down. I increase load. Load voltage decreased, and guidance system did it work. It increased voltage. So in general, this thing tries to keep load voltage stable. Ah, you wait. see my toy. It's my funny toy, rheostat with the motor. Take a look what I have. Rheostat, motor driven. This is analog to digital converter. This is brain processor. It's what's going on inside. It has two voltages. One is set point, is set by this tiny knob. Okay. It's a small rheostat. And another value is from second channel. It's a low voltage. Mm-hmm. The system tries to keep them equal. For example, I drop load. I drop load completely. Mm-hmm. Look what happened. I increase load. Voltage decreased at some moment, and system compensated it with the movement of the rheostat. If I change set point, what I got here, for example, I'll set to approximately 100 volts. Goes, down. And it's stable. I decrease load. Voltage increased and system decreased it. I let's say drop up load. Nice thing, isn't it? Nice toy. It's voltage stabilized. But how will it react to the change of primary voltage? I'll set to something ground. $143. Okay, let's say it's 140 volt. 140 volts, current 0.47 amps, and consumed power, it's a 60 watts. It should be multiplied by 2. But okay, third division. Now, let's see how it will react to change of the primary voltage. I'm setting voltage to 240 volts. Mm-hmm. What's going on? See, 137 and 170 volts. Okay, 180. Okay, this one is more precise. 180 volts. What's doing? Increases until same power up 230 volts. And guidance system pushes it back. To same voltage down, and it pushes up.
I think it's also same.
For the system, change of primary voltage is the same but change of load. System tries to keep voltage stable. I increase voltage on the primary side, and control system pushes it down. I'm changing voltage, but load power remains the same. Losses may change.
How can the system is stabilized using this?
This part converts analog values to digital form, And this is brain. It's a processor. It's what's going on inside. It's a key element of program.
So you are set the limit left and to right.
So yeah, I have limiters.
Okay, I understand.
See, we have to limit.
That's limit, yes.
It just walks to left, walks to right.
Okay. Up and down, move left, and up and down, move right. Yes. Again, to stabilize, decreasing.
Hold. Okay. This so. It's dying.
What? It's very good.
Don't want to use it. Okay.
Yeah.
Use this. I will make my screen possible. Nice toy to play.
Yes. You religion in the party? No.
Want to take a picture?
Yes, this controller.
It's all
I think
Mitsubishi.
this is very old controller.
Yeah, in its time it was one of the best.
Oh.
Very reliable and it's quite reasonable price. It's FX3U.
Okay. This is based by PIC or it's like controller.
Yeah, simple programmable logic controller. It has good selection of addition modules, expansion modules. Simple to program and a reasonable price.
Reasonable, yes.
Okay, let's go forward. Why I'm showing this? What's the idea behind my toy? Why I'm showing it?
The temperature is stepper motor temperature or what temperature you measuring? Temperature. Heat.
Yeah,
But the program is on the heat is measured.
the program measures voltage. I don't have heat channel.
But they're showing that the temperature is 30, 40. The program is showing the temperature also.
Sorry. Wait. TMP means temporary. Wait 1 second. Maybe. There is
No.
TMP.
It's a terminal point.
No, it's a temporary.
Temporary.
I use TMP to designate of temporary. Well,
Okay.
oh, it's just an interim value for ADC values. It's a small trick. See when I can also attach a monitor, a small touch screen. So I left temporary variables
Okay.
If I touch the screen, they will get names and they will be used on screens.
Okay.
It's how to say, it's a dummies for future.
Okay.
The temporary variables are not important.
Okay.
It's not a temperature, it's a temporary variable.
Temporary variable. Okay.
And H indication lamp, H indication, L lamp, Y yellow. Actually, I don't know why this sound. I can't remember why I put it here.
Okay.
Because I don't use it in project, it's 100%. It was for this nice touch screen.
Okay. So
But
you are using the temporary.
it's a dummy for future users.
For future use.
But there was one problem. Screen uses the same port what I use for programming.
Okay.
That's why it's not here. Maybe one day I will put it.
Okay. Now that this is for the today class for only understanding for this, right?
It's actually it's a toy illustrating a closed loop regulator.
Okay.
But now let me explain why this toy is here.
Okay.
Why? It's a funny demo just to play for, but if we take a look on a way how city network or middle voltage network is connected to 110, 115 and so on to high voltage network, we will find one interesting moment. This transformer, ground star, delta, let's say 10, 11, 12, whatever, kilovolt bus. Middle voltage bus. From the middle voltage bus, via a special measurement transformer, 100 volts measured voltage is taken and taken to the voltage control device. Voltage control device sends a command to the special actuator. And what this actuator do? It switches taps on the transformer primary side. The star connection of this transformer is not, let's say, monoline. It's changeable. It's made with the top, with the step. Steps are different, very typical, 1.25%, maybe smaller, maybe 1%. And range from 20 to, there are transformers with the range of plus minus 50%, can be ordered. 12, 15, 20, 24% switching range. And in step, 1%, 1.25%, very popular value is 1.25%. So transformer, this large transformer ratio can be changed. For highly variable loads, like railroads, special kind of transformer where it's a primary transformer and in series attached variable can be used. I saw them once in not only in two pieces, but on a carriage track to use on railroad. It's a kind of mobile substation. Can be put anywhere where needed and power all this railroad stuff. but it had not 10 but 24 kV on the side is for traction. But wait a moment. Voltage controller tries to keep constant voltage at this bus. We have a load variable. Few people work at night, so at night time we have load decrease. At morning, here, for example, in our, let's say, climate, I observe a very clear thing. When children should go to school, it's timing. Children goes to school. Hour before, wake up, switch on teapot, switch on our cooking stoves. Children goes to school. So it's a morning peak of load. Then load decreases, and again it rises at the evening time. Again, children come back from school, we need to cook, and so on. So load is variable. If just left voltage uncontrolled, unregulated, it will go down at the peak hour and rises above any reasonable level at night time. So clients will complain. Public service regulator will find company. It's not a good idea. Voltage controller keeps voltage at a city network at a, let's say, in a allowable range. What did we solve on my toy? Change in primary voltage do not change in reality load power. Yeah. I have changed primary voltage, but load power remains the same. It's because control system compensated change. Here the same thing. If we perform a calculus on high voltage network, all these clients looks like not a constant kind of current or constant resistance, but as a constant power. In more detailed look, we need to take into account limits of regulation. We may see, I don't know, like voltage, for example, reactive power looks flat and again rises. And this flat is determined by this flat area determined by the range of control transformer. But at the first step, at the first approach, we can assume that we have no abnormal situation and we are within range of control. If we are within this range of control, good idea, reasonable idea is to look at load as a load with constant power, or so-called constant volt-amps load. My toy is example of constant volt-amp load from the primary side. How can we? We need to do something about it. What means do something? We need to perform a calculus for such a load regime. And usually we have two goals. We can have two goals. One is determination of so-called power flow. Who's selling electricity and who's buying? What will be flow of energy? And second is so good for KPI, no? Key performance indicator. What's efficiency? What are losses? Losses losses are anti-benefits. More losses, less benefits. If, for example, in our climate, I show results with technical losses above 5%, it's easier to throw my head back when the month benefit. I will receive nothing in benefits. And possibly in very foreseeable time I will seek for a job. Say, I will be happy customer of employment agents. So, in such calculus of such network, when we deal with fault regimes, we are seeking for values to calculate protection devices. It has no, it goes to 3. But in calculus of such kind of normal regime, we are very often we seek efficiency. We need to understand network performance. In such case, when we look for efficiency, we assume what? We are within design or operational range of regulators. So what can we do? We need to conduct some kind of model, digital model, numerical model to perform our calculus on. And this model will have one important let's say, property. What kind? So if load can be characterized with its full power, I will, to make it simpler, I will assume what both loads and generator has set of constant power. In reality, generator can be set or in PQ mode, when it true constant power, or in PU mode, when they set for active power and voltage absolute value. Real generator can be or PQ constant or PU constant. Real power plants. For simplicity, I will take this one. It's just to simplify notation. So, for S vector, generator will come with plus and load will come with a minus sign. Now, trick. Trick is to substitute load with the controlled power, controlled current source. With current being, what should be current? Current is conjugated load power divided by square from 3 conjugated load voltage. For generators, the same, but current source will be supplied. Controlled current source. Why this? Simple complex power is voltage multiplied by conjugation of the current. But first, we have three-phase network. That's because it's free. Multiply triple. But that's not all. I don't know how in your country we use line voltage in such calculus. It's simple tradition. You can use phase, you can use line. It's not a problem. But simple tradition. And tradition asks to calculate for line voltage. 110 kilovolts is a line-to-line voltage. 10 kilovolts is a line-to-line voltage, not line to ground. If we use line voltage, we need to put a square root from 3 here. To obtain, for calculus, we need phase. But tradition is tradition. If you do not obey tradition, everything will fail. Yeah? Yeah. So, if you extract current from this, you will get this formula. You will get conjugated power divided by square root and conjugated voltage. If I do in such way, I can write a system of equation in form of current balance. It will be nodal admittance matrix multiplied by nodal voltage vector equals to du inverse plus nodal voltage. What's the D? D is a diagonal matrix and its elements are node power divided by square of 3 and conjugated. You need to change sign on an imaginary member. This one is a vector of conductance between nodes and a base node. And this is base node voltage. This one is needed because here in such calculus, base node is not ground. Base node or slack bus is a larger power plant. Actually, no, it's not. It's usually a large power plant, but it's a power plant with active voltage control system, keeping high voltage network voltage. It's a total, but someone need to take care about voltage at a high voltage side. Power plant equipped with a voltage control system will be your slack bus. In our case, more that someone need to take care about frequency control. Someone need to balance a power, energy balance to keep. Anyway, we need to. Someone need to keep voltage. It's a power plant with a voltage control system. Acting in way we keep voltage. We will we will close the balance. Balancing node or slack bus. In the network calculus terminology, it's a slack bus. So base node voltage is not zero, and if it's not zero, slack node also can be a source of energy. If it is an source of energy, I cannot set it zero, and I need a vector containing conductivities between nodes and base node. You don't need to conduct it. It's much easier to calculate it, knowing what base node conductivity vector elements number A is a sum, and you have to change from 1 to number of nodes of nodal admittance matrix. number of nodes. Yeah. We see an equation system. Is it system linear? In our previous calculus, we saw a linear nodal voltage system. This one is not linear. It has voltage on the both sides. It can be solved analytically, but it can be solved numerically. Good news, it can be solved numerically if we use any of the iterative or sequential approach techniques. We will have next voltage as some function of the previous one, yeah? The previous step. That means what I can use, it's physically it's one voltage in one node, yeah? But for calculus process, I have previous, pre, and next, and forward. It means what I can use previous one to calculate something for the next one. In my case, currents. I can organize a specific form of the Seudel process. Oh, we used Seudel.
Professor, in this system, the primary current and the secondary current are also similar?
What means similar? We have transformer later.
So it's a similar.
What means similar? You have transformer in between, and here they are similar.
Ah, okay.
It is difference on internal consumption. In reality, difference will be what? Transformer magnetizing current. Losses in steel, losses in copper. What I'm doing? Yeah. I'm going to write an formula for Seudel, let's say, process. For classical Seudel's process, what we need? We need a C matrix with A divided by A E, D vector as I, and X next is sum from 1 to I minus 1 I next plus sum where let's say m changed by I plus 1 to the number of equations m and previous plus di, it's for all I starting from 1 and ending with the number of equations. We can modify this to our purpose. See the modified version. In modified version, this transfer matrix should be conducted from or derived, let's say derived from the nodal admittance matrix divided by I for each I from 1 to number of nodes and for each I from 1 to number of nodes. We will not conduct D vector because it will be changed. It changes on every step. Our key formula looks like this. Voltage in the I node next to 1, it's a complex value, will consist of sum, let's change from 1 to I minus 1, C I U next, plus sum plus 1 to the number of nodes and previous plus this part is the same what we saw in our AC network modeling. This part is quasi. Addition is this part. Here we will have VII divided by conjugated voltage at node I plus base node conductivity vector element I multiplied by base node voltage. This should be done for changing I from 1 to number of nodes. Here is the form of what? Of modified Seudel technique. Here I can also write conjugated power and I naught divided by square root of 3. There is no difference. So here, what's the idea here? On each step, currents representing loads and generations are calculated using previous voltage. In case you have more complex law of control, anyway, substitute this with the current being function of voltage you need. You can put here any control law and it will work. It's a way to solve this nonlinear problem. Now, how can we control precision? This is clear? Not very optimistic, I'll say. Precision, very simple. It's a max absolute difference between step voltage. It's easy. Next element of the puzzle, let's say, we will need a power flow. What's a power flow? If you have generation line, you put a wattmeter into line. This is so-called branch power, and if you have more advanced meter, branch full power. Are we selling or are we buying? So, power flows. Here for power flow is voltage and node I multiplied by branch current conjugated branch power in the branch and also multiplied by square root of 3 because we have free phase and line voltage. This is in force if it's not 0. I from 1 to number of nodes and from 1 to number of branches. has the element of power flow vector. It's a money vector. Another one is a difference. Let's say 1 d pz delta. It's difference. It's loss in line. What are we losing? Our internal economy. Can be calculated as 3 multiplied by current and multiplied by conjugated current in the branch. This will give voltage drop, and voltage drop multiplied by conjugated current. Don't make a mistake, not a square of the current, but current multiplied by its conjugation. From 1 to the number of branches, so it's a number of branches. Where is my syllab? Where is my syllab? I would like to show this code. I would like to show this code. I will try to get it on a large screen. So, yeah, got it. So what I have here? Something wrote in 2018. Clear picture of values, length of lines. Yeah, it's lines in kilometers.
Okay.
I have a kind of I have something like this with load, and here was a generation. And also base here is the top. Very simple schematic, it's not important. 6 line. For simplicity, I assume that all lines are made from the same wire, and for 110 kilovolts, very common resistance is 0.2 plus 0.2 active ohm per kilometer and 0.4 reactive per kilometer. I took page from some of the Riga line, so it has 0 to 1 active ohms per kilometer and 0.39 reactive ohms, inductive ohms per kilometer. So here I'm conducting resistance vector. My incidence matrix, branch to nodes or nodes to branch. We saw it before. Measurements, number of nodes, number of branches, and here power. For this kind of task, never ignore reactive power. It's changed a lot. So I put active P, active Q, active P, Q, pay Q, pay Q. I use a complex function to combine them in one complex value. And here is my power vector. Load with the minus sign and generation with the plus sign. Yeah?
Yes.
In blue. Square root from 3 and voltage of the base node. Here I compose actually I need the D matrix is a pure diagonal. So I don't need to fill all the zero. I keep only main diagonal as a one vector. Very simple inversion of the resistance matrix, and I will need diagonal conductivity matrix.
This is Seudel method. This is Seudel method. You find the power flow or
110 kilovolt network. It's okay for this technique is okay for any network with regulated load. If you need higher voltage, the line capacities are playing. It is not a problem. Just add capacity branch as capacitance. No problem, because it's derived from the classical nodal admittance technique or this nodal voltage method. No, it's suitable for any network with regulated load. Okay, what's next? This one. What's in this row? I assume that node voltage are not far from the base. So, if I start my sequential approach process from something reasonable close to the solution, I will save time. This part, I need very simple. I need transpose incidence matrix for this nodal admittance matrix. It's a matrix of my system. Here, this part, I make or I calculate admittance or conductivity between nodes and the base node. This is simple preparation for Seudel technique. This, this classical C matrix from the Seudel technique. And here is my solution itself. What do we see here? Repeat until precision is reached. Number of this iteration. This part. For each node, sum number 1 from the Seudel, sum number 2, and this part. Currents recalculated at each step as a function from previous voltage. This is for precision, what I select, and I'm putting my voltage in place. Solus guides its number of steps, voltages, branch currents. Strauss means branch current, power flow. This part calculates power flow. If I'm taking nodes by one, I'm taking branch by one, and if they are connected, so if incidence matrix element is not 0, I calculate branch power flow as a square root from 3 multiplied by node voltage multiplied by conjugation of the branch current.
Okay. Yes.
And jaudas posmus, power flow,
Yes.
losses.
Branch losses.
Yeah, branch loss. I took branch by 1 and here it is 3 because 3 phase, branch resistance, branch current, conjugation of the branch current. The car, it's in Latvian zudumi kopa, total losses. I calculate total loss. Here I will, here I calculate total load. I don't need to think. And this road, this road will give me efficiency factor.
Efficiency, okay.
TLK means tīkla liederības coefficient. Efficiency factor for the network. K, coefficient is a factor. L, liederība, efficiency. And T, tīkls means network. So, TLK is a network efficiency factor. Let's see what I will get. Oh yeah, here we have. I saw solution took 30 steps, 3 and 0.
So,
Nodal voltages, 114, it's in kilovolts. Branch currents in kiloamps. Power flows by branch in megawatts. Megawatts and megawatts. It's in mega.
mega, okay.
Yeah, it's this section losses
Losses
per branch.
per branch, okay. This is a
Total losses 3.26 megawatts and efficiency factor 96,999. It's not the best one. Actually, this threshold is on 5%. But for 5%,
5%.
if I show 5%, I think next day I'm fine. Really, it's on a good digits are losses 1.2, 1.5, something like this. If I'm within 2.5, I will get my bonus.
Okay.
If not, see, these top bosses, they always are asking for improvement in KPI. Key KPI, technological losses. It's for net, it's profitability, because state calculates tariffs or this tariff control board usually calculates tariffs on the base of 5%. Everything above 5% is a profit for the company and our bonuses. So as you can see, it's a quite simple addition. It's quite simple to modify existing Seudel technique what I used in previous. You can see it's a in general it's the same Seudel I used to solve the electrotechnics theory tasks, but modified to calculate current on each step. Not just currents are not just defined, but recalculated, knowing the load characteristics. Oops. Stay. Oh, we have one viewer on the line.
Thank you.
Very possible. What I need to do? I need to put let's try to get in. Come on, let me in.
Professor, if I am not able to come to class, is possible to attend online?
Why not?
Okay.
Why,
And,
why I'm doing all
okay.
this job?
If I'm not able to come next week means I attend a YouTube. But what about the attendance?
You can attend comment. I'm here.
Put the attendance.
Who cares about it? You think real someone checks?
I'm sorry.
You think the real someone checks? All the
No.
sentence check?
Oh, really? It's not a check.
It's not. You know what? I don't know. Maybe the department.
The department maybe check. Yes.
Yeah.
No. Okay.
You know what this means? Herrings. Herrings. Examples. Where are all my examples?
No need to attend because that's absolutely no sense. Paste it in the word. Yes, yes. 23 December. 20 December. Task 1, 2, 3. That's all right. Okay. Maybe I fetch me something related to the task.
Yeah. I have a lot of.
So you upload it?
Yeah, I did it. I did it. Now what else I need to do? To get somehow this attendance charts.
Yes.
Plugins. Here. They is
Per week 200, 250, 300 something. But still no, I'm not interested working with it. I'm trying some companies. Like our core.
okay. Who want to see his name?
No, I'm searching the two things. No, for me. If I select it, I will tell you which company and how to approach it. I am applying for the electronic manufacturing group.
Is it correct?
Yes.
Yes.
Good.
Oh,
I don't know. Maybe someone changed his name.
you remember my name? That's something.
Some, you know, things. Who's guy there? Not a hamster. Yeah. Where things happen, strange thing happens, everything happens. You come one day, oh no, I'm not the guy X, and today a lady Y. Big bang. something familiar.
Yes, yes, I need this.
Yeah,
I'm confusing
Yeah.
with this. I have this exactly. Okay.
not, yeah, it's
How I can make the young and young?
how? Take this sheet,
Okay.
select one of the
Base
nodes which will become a base,
Maybe anyone I need to choose, right?
anyone.
Anyone.
Oh,
I'm sorry. Okay. Can I
anyone you,
choose
anyone.
this? Anyone. It's not a
As,
problem.
yeah, this will be base.
Okay.
Usual model with trend. Yeah, now put numbers to other nodes as
Okay. 1,
you as you want.
2.
This will be
Three.
3, let's say
It
4,
will be 4. Yes.
and it's 4. Now,
It will be 5.
yeah, and this will be number 5.
5.
Now
I need
you
to put the values.
you can also branch need numbers and direction
Okay, I need to put any direction. It's not a.
as you wish.
Yes.
You can throw coin. You can I don't know, spin something.
Okay, I need to.
It's absolutely free.